I'm going to stop sharing my screen and I'm going to introduce our speaker tonight because I am super, super happy about this. Um, Chelsea Troy is a software engineer and a teacher and a writer, and her blog is one of my favorite reads because it has been one of the most impactful things on my career. I've actually built a talk based on one of her blog posts, and I attribute it to her every time because she has a really unique perspective on technology. She incorporates humanity into just about everything that she writes. It is so cool, and it is such a privilege to have her come and speak to us. Tonight, she is going to be talking about what we can expect from AI as software engineers. And Chelsea, I would love for you to take it away. Thank you so much. I'm really, really excited about this.
Oh, thank you. I'm honored. That's such a lovely introduction. I really appreciate it. Thank you so much. I'll go ahead and share my screen. Hopefully, y'all will be able to see my slides. You should see a Firefox window that says, "What can we expect of
Yeah.
LLMs as software engineers?" Can folks see that?
Yes.
Amazing. So I'll get started on this talk. I'll tell you briefly that the origin of this talk came out of first my day job and then out of my teaching. As Jacqueline mentioned, I teach at the University of Chicago. I teach masters in computer science students. One of the classes that I teach there is Python programming. Now, as you can imagine, the ability to put the questions that I ask students to do for homework into ChatGPT and then get the answers to pop out has significantly changed the way that I need to design my classes. But what's interesting is that um, in speaking to students about the availability of these tools and about what it means for students' lives and their careers and their skills, it turns out that they're thinking about it a great deal more than that. It's not just to them sort of a homework generation object. It's a thing that they've heard a lot about that carries all this mystique, and they're given these sort of dual expectations from the tech zeitgeist around AI generally. The first thing they're kind of told is that if they learn to use these tools, it's going to make them super effective and it's going to be amazing and the world's going to be great and there's nothing they can do about it, so they might as well learn it anyway. And the other thing that they sort of learn is that the availability of these tools means that they are out of luck from a career perspective. And so a lot of students are having this sort of like existential crisis on top of this great promise that's at this point snowballed on top of a lot of their other concerns coming out of the pandemic, dealing with family, trying to get their master's degree after an undergraduate education that was significantly different from those of the people who came before them because it happened during the pandemic times. There's a blog post about the way that I think that this landscape has impacted students specifically that I'm happy to share at the end. But this talk came out of witnessing that with my students and wanting to be able to give them something concrete, a starting point that they were able to use to understand how these technologies work, in terminology that would be familiar to them so that they could gauge appropriately how they should expect to use the tools and when they could expect those tools to succeed or fail. So that's the premise of the talk. And so we'll talk about those things. We'll talk about how large language models function. I'll show you how the models themselves fit into the larger product that you probably know as ChatGPT or Gemini or Claude or Devon or whatever the one is that you use. Then I'll spell out some conclusions at the intersection between large language model use and professional productivity. And then at the end, we'll summarize takeaways because as much as I hate writing conclusions for my blog posts, I think they're very important in talks. So we will have one. But I'd like to start here because I think this discussion will make more sense with a concrete example. This is a bug I've come to refer to as Strawberry Gate that first made its rounds on social media in the back half of 2024. If you asked how many R's are there in the word strawberry, many generative language tools would respond with the answer two. So there's a short exercise in my O'Reilly workshop about large language models that asks participants to try this themselves. And I've had folks run this on Claude, Gemini, various iterations of ChatGPT. I've had people report every integer between 0 and 3 inclusive as the answer to this question, according to their large language model product of choice. It seems like a simple question, though, right? Count the R's in the string strawberry, and you'll find that there are 3. Surely the tool to which large swaths of the population have begun to outsource all of their prose tasks could handle such a trivial counting operation, right? So, why do we see this happen? The answer in a single word is context, but I'm going to explain what I mean by that because I think popular discourse has a tendency to use this word in a few different ways, and I want to make sure that we're clear. Large language models are trained on prose text that their build teams were able to scrape from the internet. It is from this body of knowledge, chiefly, that these models draw their response capabilities. On the internet, people don't ask about the spelling of strawberry in a vacuum. Usually, when a spelling query like this comes up, people aren't referring at all to the first R in strawberry. When they ask how many R's are in the word strawberry, this is usually a person who is learning to write and spell in English. Now, English is not even close to a phonetic language. I hear that there's a Dartmouth professor who refers to it as the shower drain of languages, and I think that's pretty apposite. English is not like Arabic, Serbian, or even to some degree Spanish, in which you can more or less sound out a word based on its spelling. English spelling, instead, is all over the place. And a word's pronunciation doesn't necessarily tell you whether it contains a doubled consonant, such as the two R's that appear next to each other in berry. Now, this is partially due to the fact that English is a disorganized melange of loanwords and calques and vocabulary of diverse origin. However, it's not unique to English. This map that you see on screen shows the words for berry throughout Europe alone. And even among those places that do pronounce it berry, you'll notice that the number of R's is not consistent. When someone talks about the R's in strawberry, or rather asks about the R's in strawberry, they generally want to confirm the presence or absence of the doubled consonant. The technical answer to the question, how many R's are there in strawberry, is 3. However, in the context of their confusion, scopes down specifically to the number of R's that appear in the berry part, we're looking at a doubled consonant, 2. Often, the answers that these questions receive from people online recognize and account for that context. And the text of their answers is what large language models are trained on. So, to understand the role of context in the training of a large language model, I want to introduce you to a much simpler model, the Markov model. Are folks familiar with Markov models or Markov chains? Excellent. I will introduce you. This is another somewhat simpler machine learning model type of thing that we can sometimes use in order to make predictions about sequences of events. You see one represented here on screen, and I promise that in about 2 minutes you will know exactly how a Markov model works. The model has states, in this case, the weather conditions, sunny, rainy, and cloudy. It then has transition probabilities between those states. So for example, from cloudy, there's a probability of 0.4 or a 40% chance that it's going to remain cloudy. There's a 0.3 probability or a 30% chance that it's going to become sunny, and another 30% chance that it's going to become rainy. If we imagine each of these states as 5-minute intervals, then we can say that we know the probability that it's going to be any of these 3 states in the next 5 minutes. Now, together, the probabilities of it being sunny, rainy, or cloudy over the next 5 minutes account for 100% of the options. If it is currently rainy, in 5 minutes, it will be either sunny, rainy, or cloudy. For the purposes of our example, I understand that weather is much more complicated than this, but for the purposes of understanding this Markov model, we will imagine there are only 3 weather states in the world. Now, if you wanted to predict what the next weather condition might be, based only on the information that it is currently cloudy, there's a probability, or rather, your best bet, though certainly not a sure bet, would be to predict that it will be again cloudy, because that is the highest probability at 0.4. Now, if it's currently sunny and you want to predict the next weather state, your odds of predicting correctly improve. Because the leading transition probability, that is the probability that will remain sunny, is 0.6 for that state, as opposed to just 0.4. So if you guess the most likely outcome, there is a 60% chance that you'll be correct. The transition probabilities in a Markov model make it a quick calculation for you to determine the probability of any given chain of events happening in a certain order. In fact, if you have a complete set of transition probabilities, a Markov model allows you to calculate the probability of a given chain of events happening in any order. Now, imagine you had a network diagram just like this weather one, except the network diagram contained every single word and piece of punctuation that has ever appeared in the Common Crawl. This is a crawler that collects an estimated 250 terabytes of data from billions of web pages every single month since 2008. Each transition probability points to a word that has at some point appeared after the word in the node you're looking at. The node probability represents the relative frequency with which the next word is that word versus any of the others. Now imagine also that these transition probability arrows, we call them edges, do not just connect each token to the very next token that appeared in written text. Token is a word that we use to mean any element of written text, whether that be a word or a piece of punctuation. So these transition probability arrows don't just go from one word to the next or one token to the next. Additional arrows influence the probability of which token will appear next based on which token appeared one token ago, 2 tokens ago, 3 tokens ago, etc. This is what we get from a machine learning model architecture that we refer to as the multi-headed attention mechanism. This mechanism underpins the function of the transformer and therefore the design of modern large language models. Let's look at a specific example. Here, you'll notice that I've listed out several n-grams in the left-hand column to help you visualize. Now, we're trying to predict the token n, the token in the nth position. Now, we see some options there on the magenta line at the bottom. Now, at the n-5 position, we've got a token indicating the start of our phrase. The first word in the phrase at the n-4 position is I. The next one at the n-3 position is went. Then at the n-2 position, we have to, and at the n-1 position, we have the. So on that magenta row, you see some options for what the next word might be. Store, movies, car, apple, parrot, etc. Now, in the network I've described, you'd have a lot of options because people will have said in the Common Crawl, I went to the, with all kinds of words as the next one. But this small set is going to help get the idea across. Below each word, you see a prediction weight. Larger weights for words that appear more often in that position relative to the given inputs. Smaller probabilities for words that appear less often in that position relative to the given inputs. Let's say for now we're generating text by randomly selecting from among the tokens with the highest prediction weight, and in this case that's store and movies. So we're going to select store. Here we are, store selected. Now let's move on to predicting the next word in the sequence. Next to the first set of inputs here, I've added a second set. This one has the start token at the n-6 position instead of n-5. And the word I at the n-5 position instead of n-4. All the words have been bumped up one position so that we can add store that we selected in the last round to our sequence in the n-1 position. We now have new options to select from. I went to the store too. I went to the store and I went to the store apple. Note the very small prediction weight on this option relative to the options that include tokens that would make a lot more sense in this phrase. Now, what sorts of tokens might we expect a pattern like this to do especially well at predicting? We would expect it to do well on tokens that exhibit a very strong pattern of where they appear. Things like preposition words, such as at, or by, or in, or of, or punctuation, like commas, or periods, or colons, or semicolons. These sorts of words are highly contextually linked. That means that their appearances follow a strong pattern. Now, here's the problem. Most tokens don't get their position in a phrase mostly or wholly from the pattern of the phrase. Instead, they get their position from the meaning of the token itself. The token store, a place where we go to select items off of aisles and buy them from a cashier, means a different thing than the token movies, a place where we go to watch feature films on the silver screen. The massive network derived from text that I've described to you picks up on these patterns. When words have different meanings, they are what we call denotationally distinct. That means they have different denotations, distinct definitions. Okay? And they usually appear, words that are denotationally distinct, usually appear in different contexts. Say, I wanted to say, I needed to buy some apples, so I visited the blank. It's clear to you and to most of the people typing text on which large language models are trained that the next token has to be either store or something very denotationally similar to store. Denotationally similar words can usually appear interchangeably in the same pattern without affecting the meaning of the sentence. I could say, I wanted to buy some apples, so I went to the store, or I wanted to buy some apples, so I went to the market, and those would be words, those would be phrases that had relatively similar meanings. They would both make sense. I could also say, I watched the new film on Friday at the movies, or I could say, I watched the new film on Friday at the cinema. Whether a generated sentence uses the token movies or cinema in this case doesn't change the meaning of the phrase at all. Where generative language models run into trouble is in situations where choosing a word based on the context isn't enough to get it right. That is, in situations where tokens are denotationally distinct, they have different meanings, but they're contextually identical. They appear in the same patterns. Which words do that? Well, often numbers. I have 3 apples, and I have 5 apples, and I have 4,000 apples all mean very different things. But the interchangeable tokens all appear in identical contexts. You know some numbers that mean even differenter things? The section numbers used to partition legal text. Section 108A of a legal code says a completely different thing than Section 204B, but they're both referenced the exact same way. This causes lawyers to run into trouble when they ask ChatGPT to help them reference legal precedent, and they end up citing sections that sometimes don't even exist. Proper nouns are another one that can trip up a large language model quite easily. It matters whether Miss Peach or Sergeant Grat or Mr. Green did the crime with the candlestick in the kitchen. Accusing any one of them makes grammatical sense, but the phrase doesn't mean the same thing. Now, a lot of times when it comes to proper nouns or numbers or dates, generative models can get it right. And the reason for that is that context often fills in to suggest the right thing. Here we have an example phrase. Justin Bieber was born in, with several options. Now, he certainly wasn't born in apple or parrot, but the years we see as options here have higher prediction weights. The correct year here, 1994, has by far the highest prediction weight, and that happens because the inclusion of Justin as an N-X token, followed immediately by Bieber, and then followed somewhere after that by born, overwhelmingly results in the number 1994 appearing in the online discourse. And this is what I mean by that multi-headed attention model. We have got arrows coming from Justin and Bieber and born that all indicate relatively high transition probabilities for the token 1994. Suppose we had instead this situation. We're trying to complete the phrase, the law firm Johnson and blank. A quick Google search immediately dredges up half a dozen law firms whose names start Johnson and, but then end with a different surname. Which one should the model reference in its generated text? Context alone may not be able to provide an answer, so the selected token here could be wrong. This is why you have to verify facts that you get from a large language model. A phrase that sounds plausible is not the same thing as a phrase that is objectively true or correct. Numerous lawyers, doctors, and software engineers at this point have gotten tripped up in courts of law because they placed the weight of their professional credentials behind a claim or an action that a chat UI suggested to them that sounded believable and turned out to be a fabrication. How do you fix this? The field has begun to answer this in various ways, from retrieval augmented generation to supervised fine-tuning. Both of these are sort of specific patterns that we use. I'm happy to talk about them later if folks are interested. However, frequently, the quickest and most pragmatic solutions happen outside of the generative model itself. That brings me to the difference between a large language model and a generative AI product. Two concepts that I think the discourse tends to confuse them, but they're actually different things. This orange oval represents a base training model. For our purposes, the sort of language generating transformer model that I've talked to you about so far. A base model like this requires massive amounts of data and computing resources to train. This is the reason that you see no more than generously a dozen organizations training these things completely from scratch, because nobody else has the resources or the money to do it. And even those organizations are doing this step no more often than once to a couple of times a year. Even your Amazons, Googles, and Microsofts don't have the resources to do this step all the time. So they ration their base training steps, and then they build on top of the base trained model that they get from that attempt. Once you have a base trained model, what you've got is a program that can take in a grammatically intelligible sequence of input tokens and output a grammatically intelligible sequence of output tokens. But it's not the polished question and answer bot you've come to know from typing things into ChatGPT. That part comes from the next step, the fine-tuning. Now, colloquially, when blog posts and programmers at conferences talk about fine-tuning, a lot of times they're talking about how they took a finished model, usually Llama from Meta, because that's the one that you can access easily online, and they're passing it a paltry tome of subject-specific research or like all the code off their private GitHub org. The fine-tuning that happens during the model production is much more substantial than this and moves the model from the sequence to sequence phase to a question and answer phase. Often a big part of this is having human evaluators select the best option from 3 answers to a given question and provide this as a feedback loop to the model. And in fact, some companies have already begun to outsource parts of this step to you, the folks who are using the model. Has anybody here given a prompt to ChatGPT or another large language model product and seen that a couple of results came back and you were asked to select the result that you found the most useful? Yeah, this is part of this fine-tuning step. This is you being included as a client in the fine-tuning step for these models. Now, this fine-tuning step requires orders of magnitude less compute power and data than the initial training phase. And the same companies that execute the base training 1 time or maybe 2 times per year might do this fine-tuning step on like a weekly basis. So at this point, the model can accept a sequence of inputs and give a sequence of outputs that reasonably resembles an answer. The early days of language generation products could ship more or less that. The problem was that we, the consumers, had a disconcerting habit of confusing the output sequence with an actual reasonable answer. Consumers with software engineering background, for example, could not collectively agree on the conclusion that When they asked a large language model product to find the bug in their code and the output said, I ran the code for you and I think your problem is blah, that had not happened because the LLM had spontaneously generated a compiler and a runtime and actually run the input code. It had said that because it had been trained on internet text, where questions like the one this programmer had asked often receive responses on Stack Overflow and similar sites that start with the sequence of tokens. I ran your code for you and. If professional software engineers confuse language generation with language understanding, and they become upset at the suggestion that a sequence of output tokens are a lot less likely to factually describe the spontaneous invention of automated compiler generation than they are to just be false, how can we expect better intuition of the general populace? Conveniently, tooling rapidly improved. Now, generally, when you use a product like ChatGPT, your input doesn't get fed straight into a raw large language model whose output comes straight back to you. Additional models surround and support the language model to provide you with answers that are more likely to be what you want. Consumers use these tools to accomplish all sorts of tasks, and supporting models help adapt to those circumstances. For example, pardon me, large language models, like most machine learning models, accept a number of hyperparameters. In the case of large language models, some of those hyperparameters guide how the model generates sequences of output tokens. Most machine learning hyperparameters help to configure either how the model is going to be trained or how the model is expected to make predictions. They're called hyperparameters because the parameters in a machine learning context are usually the input columns of the data that we have trained the model on. So in the case of large language models, there are two hyperparameters that make really easy examples. They're called temperature and top P. Temperature and top P, I'll elide the specifics of how these parameters work, but long story short, higher parameters, or rather higher values for these hyperparameters, make sense for working with a model on creative brainstorming tasks. Lower values for these hyperparameters make more sense when you're looking for more rote or platitudinous or logical output. The user interface of these tools doesn't let you set these hyperparameters for yourself. Instead, supporting models analyze your query, determine which of these two types of task your query is more likely to represent, and then set the hyperparameters on the large language model to give you the output that is the most likely to help you. Even more recently, these products have attempted to resolve some of the hallucination problems of large language models by adding supporting models that identify the tools your query would require, and then including those tools in the product. If you ask a math problem, for example, instead of outputting a sequence of grammatically permissible tokens that look like a solution to the math problem, a supporting model might identify that this problem merits a calculator and attempt to plug the figures into a calculator API for you. If you ask a coding question these days, particularly for a common and well-supported language like Python, a supporting model might identify the merit of a compiler and a runtime and plug in the code you provided. Retrieval augmented generation, or RAG, also works this way. I talked to you just a little bit about this a little bit earlier. The way it works is that we pass a model a bunch of documents from which we would like an answer. The product runs a relevancy search to associate the input query with specific passages in the RAG documents, that is, the most relevant ones for answering your question. It then appends those passages that receive the highest relevancy scores onto the end of the input query. And that whole input query, your question, plus the relevant passages from the body of documentation, all gets passed to the language model together. So now you have some better context as to what precisely is going on when you type a query into the user interface of a generative large language model product. You have a sense of what happens inside of there, and that And that understanding helps inform your intuition about what these models are likely to get right and wrong. You also have some idea about the layers that surround large language models in a product. When you go to the website ChatGPT, you're not interfacing directly with a large language model. Instead, you're interfacing with a software product, much like the ones that you and I build, that interacts with an API for a large language model, as well as a variety of other APIs to put together a complete offering that hopefully can take your question and give you a useful answer. Although you should always verify the output of a large language model, and you are always responsible for the impact of the work that you turn in with your professional credentials attached, regardless of how much your query response is yours versus an LLM's, your intuition about how these tools work can help you use them wisely and at the appropriate times. Now, suppose we're doing that. How useful are these tools for the work that we do? I have been keeping up with research at the intersection of large language model use and productivity. And what I'm going to do now is I'm going to share with you the results of a couple of papers that I think are particularly seminal in this field. I'm going to be candid with you. I was hoping to find some kind of survey study comparing the utility of these tools based on what kind of engineering work you were doing, but I couldn't find anything systematic on this. So I was forced to do some surveying of my own. We're going to get to that a little bit later. The comparative studies that I could find did evidence some patterns that I want you to recognize for the conclusions that I'm going to draw later on. Let's start here with lost in the middle paper. A lot of workshop attendees and talk audiences see the 2023 date on this paper and then try to tell me it's too old to be relevant in the fast-changing AI space. Um, but candidly, I couldn't disagree more because this paper was among the first resources to discuss a phenomenon that remains relevant to this very second, understanding why large language models get things wrong. The paper addresses the likelihood that a model can successfully retrieve information from a bolus of context included with a query based on how large that bolus of context is, and also where in the bolus of context the relevant information appears. This is the paper that established in academic literature that big contexts, more information, make it less likely that a model will successfully retrieve an individual fact. It also established that models are more likely to retrieve the information if it appears at the beginning or at the end of the context, as opposed to in the middle. What does that mean for us? Well, it means that even when we're including a context document in our input query, it's in our best interest to narrow down that document to the relevant section as much as possible, not just ram in a manual the size of War and Peace and hope for the best. I'll give you an example from software engineering specifically. Earlier today, I was using one of these tools to attempt to make some changes to a query that was supposed to extract specific keys from an array of structs in SQL. I had the schema for the table, which has 195 fields in it. I could have pasted all 195 fields of that schema very easily into my query. Instead, I went and I found the schema entries for precisely the columns that were related to the query that I am trying to run, and I shared those as context instead, because I know that that is more likely to get me the answer that I am looking for. So let's fast forward
Great,
in
Chelsea. We have
time.
a question in the chat. Do you mind if I ask quickly?
Would it be okay if we save questions till the end?
About-
Thank you, thank you. So let's fast forward to about 9 months ago, 10 months ago, when we got a hold of this paper. It's the one I'd like to spend the most time talking to you about. It gained some notoriety in the programming zeitgeist as the 26% paper, with the idea being that it says programmers are 26% more productive with large language models than without. So I want to dig into this claim a little. First of all, the proxy metric here is number of tasks completed. And the 26 statistic is coming from the fact that the conclusions claim to have seen a 26% increase in this number. of substantive import, in my opinion, to the context from which this statistic derives is that the conclusions outright say that less experienced developers showed higher adoption rates and greater productivity gains. I think that this introduces a number of confounds to the study. First of all, less experienced developers tend to receive smaller work tasks. So increasing the number of work tasks they do by some large percentage is a lot easier than if all the tasks are stuff like spearhead this giant legacy migration. It's also the case that more junior engineers tend to receive the tasks that require the least context. This is the exact thing that we've already identified as the Achilles heel of many of these systems, remember, from the Lost in the Middle paper. A large language model can be a huge help in writing a function from scratch, given a series of tests it has to pass. But at present, these models often can't, say, identify the insidious scope issue causing a data corruption problem in a 160,000 line code base. And that is the sort of task more likely to be assigned to someone with more experience. To me, this pattern demonstrates the deepening of an existing cognitive dissonance in programming education. We teach students, train new entrants, and interview candidates chiefly on their ability to write code from scratch. But as they advance in the workforce, their actual main responsibility is usually reading, analyzing, debugging, or reorganizing code that they themselves did not write. Once upon a time, writing code from scratch comprised 90% of computer science educational assignments and only 20% of a programmer's professional responsibilities in the editor. Now, that mismatch has become even larger because the tasks that once required writing from scratch manually now often include asking an LLM to write it instead, at which point the programmer is once again reading, analyzing, debugging, or reorganizing code that they themselves did not write. Large language models have not wholesale wiped out programming jobs, so much as they have called us to a more advanced, more contextually aware, more communally oriented skill set that we frankly were already being called to anyway, just 80% of the time instead of 96% of the time. On relatively simple problems, we can get away with outsourcing some of that judgment. As the problems become more complicated, we can't. Now, I mentioned to you at the beginning of this talk the role that my students have played in the generation of this talk. Now, I'll tell you that it was my work with them more than my work on machine learning operations at Mozilla that drew me to look at how developers might work with LLMs. These students, as I mentioned to you, are going through this program at a really terrifying time to be a computer science master's student. They feel like they're on the precipice of attempting to enter an industry that the tabloids insist does not want or need them because it's busy burning the planet alive and making quick work of data privacy all over the world in desperate pursuit of an automated version of what my students are learning to do. It's my job to teach these students technical skills to the best of my ability. We also talk about ethics. We talk about the impact of tech on the broader world. And on most assignments these days, I permit my students the use of large language models. I ask them at the end of the assignments how they used the tools. Interestingly, no student who has chiefly used large language models to complete all their programming exercises in my Python classes managed to exceed a flat B as their final grade. But more importantly, by cross-referencing my students' reports of their large language model use and their course feedback, I can develop a picture of where the tools are helping my students and failing my students. Given what we've discussed so far, it won't surprise you to learn that large language models struggle especially on programming problems that address variable scope, the scope in which a variable is valid and can be called, high cyclomatic complexity, situations where we have a lot of loops or a lot of conditions, and persistent layered data models. That is, where the code that we write needs to operate from a consistent understanding of what the data model is and how the things are organized. These are the three areas in which students who are chiefly using large language models to do their homework are losing the most points. It's also unlikely to surprise you that the tools fail students when the code base the student is working on exceeds about 360 lines. In order to use these tools most effectively, students must be able to first write cohesive code, code in which the concepts that must be understood together live together, so that a relatively small chunk of code can then be passed into a large language model to answer questions. Now, the thing is that most of the code that is available to train these models on comes from patterns from GitHub. The state of programmer education and the state of programming work at this point is not exactly the picture of cohesive code most of the time. The specific cohesive part on which a student needs help needs to be able to be entered into a tool in isolation, and we largely have not organized code like that. The need for cohesive code only becomes more true as the code base increases in complexity. I wrote a compiler in Rust earlier this year. It's a language I don't know especially well, and I wanted to better understand the experiences of my students trying to use large language models to build projects in Python. I'd say the large language model reduced the amount of physical typing I needed to do by 95%. I would say it reduced the amount that I needed to know about the implementation details of compilers as well as the characteristics of Rust in order to get my compiler working correctly by about 5%. I still needed to know 95% of what I would have needed to know in order to write it from scratch, despite the fact that I was doing most of the typing, not myself. Now, I have a blog post where I discuss some more details of how I approach the use of generative AI products in my classrooms. It's the one that I mentioned at the beginning, and I'll link to it again at the end here. But I think that the findings that I have from working with my students dovetail nicely into the question that I think is on the minds of a lot of professional software engineers these days, including myself. What can we take away from what we know now about the intersection of large language model usage and productivity? I think that there are a few lessons worth writing down, and I'm going to share those with you now. The first is this: large language models are most helpful on programming problems that are specific. To the extent that we can provide a complete and unambiguous set of success criteria, we can improve our chances of getting an accurate answer. They're also helpful on programming problems that are limited in scope. We've narrowed down the context as much as possible to eliminate opportunities for misidentified relevant information. They're also most helpful on problems that are focused on a programming language with a robust sharing history. That is, a language for which there are a lot of examples available online, something like Python or Java. Now, large language models can help us identify implementation options. However, so far they don't provide an adequate substitute for judgment. The more of our job focuses on experience-based judgment, the less these tools have improved productivity so far. For this reason, subject matter expertise and contextual expertise still matter in decision making. This includes expertise in when and whether to use or trust the output of an LLM, even as an initial draft. Finally, by dint of the patterns that train them, the nature of large language models supports reproducing existing logic. They repeat the patterns of language that they have seen. They produce a sort of global average, if you will, of what the internet has to say about a topic. This can be useful when questions have established answers and when programming communities publicly adopt shared norms. But what they can't do in and of themselves is innovate. They can't break from that pattern of what's been said and taught in the past. The more newness you're looking for, the less you can rely on a large language model's output in order to give you that newness. Conveniently, of course, newness describes very few of the problems that we face professionally, especially today in a very saturated tech market where a lot of what we do is migrate existing processes from one tool to the other tool. To the extent that we build new services, even most of the actual work comprises integrating a set of pre-existing dependencies and vendor APIs together. Like we're taping together the things that we've imported. Now, the question I'll throw in here that I think the advent of large language model products is still too recent to empirically answer is that I'm not sure how today's junior programmers, aided as they are by large language models, will need to navigate the challenges that we currently use judgment and experience to manage at the senior level. It's something that I'll be curious to track as we move forward in time, but I don't think we have good answers to this question yet. So, we have some understanding of what sorts of problems we can expect generative AI tools to help us with and not help us with. What skills does the AI-enabled engineer therefore need in order to excel? So this is where the talk ventures out of the territory of theoretically empirically supported claims and into the territory of what I, Chelsea Troy, think. However, my perspective is informed by the realities we've already discussed, my day job work as well as my teaching work. So I feel justified in sharing my opinions with you on this matter. I think that there are basically three skill sets that are really important for people to work on. The first skill set is investigative skills. We need to be able to scope down the area in which we're facing a problem and learn to ask specific questions about how our assumptions differ from the ground truth. I find this to be a woefully undertaught and undervalued skill among engineers, precisely because we tend to view debugging or familiarizing ourselves with the system we're working on not as part of our work, but as a blocking obstacle that distracts from our actual work of plowing through features and system changes. I think this is an inaccurate way to view our profession. I think it's made even less accurate than it already was by the advent of tools that can plow through feature development for us, provided that we possess the investigative skill to identify and understand when and how those solutions make inaccurate assumptions and need to be fixed. The second skill set is evaluative skills. We need to be able to select from a range of implementation options based on how those options' benefits and shortcomings fit the bill of our specific situation. I think we often elide this skill set as engineers by deferring to what we've read or heard as a best practice. This works fine a lot of the time, and it works up to a point, but many of your worst nightmares made manifest in code are the results of engineers applying a practice that, while best in many circumstances, didn't suit their circumstances. I think engineers, particularly at more senior levels, need to take stock of why best practices are what they are and determine whether those reasons make sense in each situation where they're being used. In fact, I think it falls to engineers to learn to specify exactly what their decision criteria are. Decide explicitly which of those are optimizing criteria and which are satisficing criteria, and document how each of their implementation options stack up against those criteria. A large language model can tell you what most people usually say to do. It cannot tell you what you should do. But the truth is, neither can most human engineers right now. This skill set addresses that. What you see here is a screenshot of a blog post that I wrote called Best Practice is Not a Reason to Do Something. There is, in fact, a picture of Oscar the Grouch from Sesame Street in that blog post. I will leave it there until Sesame Street tries to sue me. The final skill set that I want to talk to you about is innovation skills. We need to learn to proactively search for the shortcomings of the available options and consider solutions that have not been tried before. These are precisely the solutions that a generative AI product cannot produce by handing us a global average of what the internet has to say about a topic. The task falls to us, I'm afraid, to understand how our status quo falls short and figure out what we could change to improve those shortfalls. We need the ability to proactively identify who our systems do not serve or who they serve poorly and how to fix that. I've written about this on the blog too at the title that you see here, The Oxymoron of Data-Driven Innovation. I will warn you, this piece is long, a little bit long, and also makes people angry. So I recommend getting a cup of tea before you start this one. All right. So we've got these three skill sets. I am confident that these skill sets give us greater purchase on our roles in a generative AI enabled world because I see them make us better at our roles regardless of the availability of generative AI tools. And I see the reasons for that exacerbated by the availability of those tools in development contexts. If we manage to focus on these three skills, I think we can leverage generative AI tools in their most consistently successful function as an aid to our process, to aid us in being productive, not in the sense of generating more slop for GitHub, but in pursuit of a more rigorous and compassionate and thoughtful approach to software development. So, uh, thank you so much for having